Welcome to lecture 35, where we will solve the mixed problems with series. Let's start with the example 1, first example, where we have this series sum as n goes from 0 to infinity of n to the square plus 7n plus 5 divided by n to the cube plus n to the square plus 10. Now we immediately see that an is larger than or equal to 0, and we also see that an tends to 0. So this says that the necessary condition for convergence is verified, so it might be that this series will converge, but we don't know that yet, right? Because remember that we have no sufficient condition if an goes to 0. But the just first check on the sequence an says that when n goes to infinity, an is just equivalent to 1 over n. So it seems reasonable to assume that the sum as n goes from 0 to infinity of an will diverge to plus infinity. Okay, so this is our intuition. But let's now try to prove this formally. Okay, let's provide a formal proof of this. Now that we see that an is asymptotically equivalent with bn, what we can do, we can try to apply the asymptotic comparison AC with bn equal to 1 over n. And of course, let's first check that the condition for the applicability of this criterion are verified. We have that an, which is n squared plus 7n plus 5 divided by n to the cube plus n squared plus 10 is larger than or equal to 0. We have that bn, which is equal to 1 over n. Of course, this is always larger than 0. So the last thing we need to do is see what is the limit of an over bn. And if we get this limit to be a positive real number, then we can conclude that the series built on top of an will have exactly the same behavior of the harmonic series. So let's evaluate now the limit as n goes to infinity of an over bn. But this limit is n squared plus 7n plus 5 divided by n cubed plus n squared plus 10. Of course, we need to multiply everything by n, right? And we immediately see that this is just the limit as n goes to infinity. Well, we can factor n squared at the numerator, and we have 1 plus 7n over n squared plus 5 over n squared. Then we have n to the cube, 1 plus n squared divided by n to the cube plus 10 divided by n to the cube at the denominator, all multiplied by n. And we see that as n goes to infinity, this goes to 0, this goes to 0, this goes to 0, this goes to 0. So, and we simplify things, we see that this limit is indeed 1 that belongs to the interval 0 plus infinity, so we can conclude then that sum of an will diverge, or if you like, just we can write plus infinity. Now, notice one thing, we have used the asymptotic comparison. Could we use the pure comparison? Well, the pure comparison would be something like n squared plus 7n plus 5 divided by n cubed plus n squared plus 10. Well, we should prove that this is always larger than or equal 1 over n, which is possible, but it's very difficult. Okay, it's difficult to work around this inequality. Much better to use the asymptotic comparison. Let's generalize this exercise in a new exercise 2. Let's say that we want to consider the sum as n goes from 0 to infinity. We have the same numerator, n squared plus 7n plus 5, but now we have n raised to the a plus n squared plus 10 at the denominator. Of course, we are still in the case that an is larger than or equal to 0, but this time we have that this an will be equivalent to n squared. This is the only thing that remains at the numerator, and we have n to the a in the assumption that a is larger than 2, right? So this is what we have in this case, which is 1 divided by n raised to the a minus 2. So we can conclude that if a minus 2 is larger than 1, which is to say that a is larger than 3, sum of an will diverge to plus infinity. Okay, so this is the intuition that we have. Let's, as always, try to provide the formal proof of this. Well, the formal proof is the following. We need, once again, to apply the asymptotic comparison with bn equal to 1 over n raised to the a minus 2. And so let's, now of course an is larger than or equal to 0, bn is strictly larger than 0, so we need to evaluate now an divided by bn. Now an is n squared plus 7n plus 5, and we can immediately factor out n squared, and we get 1 plus 7n divided by n squared plus 5 divided by n squared. At the denominator instead we have n to the a, and we have 1 plus n squared divided by n to the a plus 5 divided by n to the a. And now we need to divide by n, which is just like multiplying by n raised to the a minus 2. Okay? Now we see that for n that goes to infinity, this will go to 0 if a is larger than 1. And this will go to 0 if a is larger than 2, right? So let's see. We have now two possible situations for this. Suppose that a is equal to 2. Well, if a is equal to 2, the an over bn clearly will tend to 1 on top and will tend to 1 plus 1 below, right? Because in this case a is equal to 2. So this will be 1/2 that belongs to the interval 0 plus infinity. So this is enough to conclude that there is convergence. If instead a is larger than 2, we see that an divided by bn will tend to 1, which again is a positive number. So we can conclude once again that there is convergence. Now, what happens if a is less than 2? Well, if a is less than 2, let's consider once again an. An is n squared plus 7n plus 5 divided by n to the a plus 7n plus 5. But if a is less than 2, of course this will diverge to plus infinity, right? This will diverge to plus infinity, so there will be no necessary condition, which implies that the sum of an will diverge to plus infinity. So we can write simply that the sum is equal to plus infinity. Let's consider a new exercise, which is a small variation of the previous one, exercise 3. Let's consider the series sum n goes from 0 to infinity of, well, now we have n to the a at the numerator plus 7n plus 5, and we have n to the 7 plus n to the square plus 10 at the denominator. And we see that this an is larger than or equal to 0. Okay, so this term of the sequence is always positive because it will contain, of course, just the powers of n, which is always positive. And, well, we, by just the first look of it, we can say that this is convergent for a less than 6. Let's give a proof of this. Okay, let's give a proof of this. Well, first thing is that we can say that an, when n goes to infinity, is asymptotically equivalent to what? Well, we have n to the a at the numerator, right? And we have n to the 7 at the denominator, right? Which is just like writing 1 divided by n raised to the 7 minus a. So when does this series converge? Well, this series will converge if 7 minus a is larger than 1, which is to say that a is less than 6, which is exactly what we had. Now, this is still not a formal proof. Let's provide a formal proof of this. But the good thing about the first intuitive analysis is that we have now Bn to compare the sequence to. And this Bn is exactly 1 divided by n, 7 minus a, which is strictly larger than 0. So what we can do is that if 7 minus a is less than or equal to 1, well, in that case we have, which is just like saying that a is larger than or equal to 6. What happens is that the series is what? We have n to the a plus 7n plus 5 divided by n to the 7 plus n squared plus 10. So we see that now this exponent is at least 6, okay? And if we have 6, we will get exactly the equivalence with the harmonic series. If we have more than 6, 7 or more, well, in that case, the term an will diverge to plus infinity. So we have an that will go to plus infinity, so we have no necessary condition, so we can conclude that an will diverge to plus infinity. If instead 7 minus a, okay, well, the other situation is that 7 minus a is larger than 1, okay, which implies that a is less than 6. Let's see what happens now. Well, in this situation, an will tend to 0, okay, which is, okay, the necessary condition is satisfied, but still we don't know if this is convergent. Now, we can rewrite an as always with an a that multiplies 1 plus 7n divided by na plus 5 divided by na on top, and then we have n to the 7, 1 plus n squared divided by n to the 7 plus 10 divided by n to the 7. And when, of course, we also need to consider bn, which is n to the 7 minus a here. And once again, for n that goes to infinity, this will disappear, this will disappear, this will disappear only if a is larger than 1. So we need to include also another condition here, that a should be larger than 1, and this will go to 0 once again. So we have that this limit in the end is going to be just one that belongs to 0 plus infinity, so we can conclude that there is convergence. Exercise number 4. Let's consider this interesting example. N goes from 0 to infinity of 5 to the n plus 8 to the n divided by 2 to the n plus a to the n, okay, where a is some real number, and well, let's assume that a will be a positive real number, okay, so this will belong to R plus. Now, by the first look of it, we can say something. We can say certainly that an, which is the sequence, of course this will be larger than or equal to 0, and not only this, we can also say something more. We can say that this is convergent, okay, for a larger than 8. Now let's prove this fact, okay, but how could I say that? Of course, if we have a larger than 8, we have this sequence that will tend to 0, first of all, so necessary condition is satisfied, and we can just apply the root criterion, and we'll see immediately how this goes. Okay, so let's give a formal proof of this fact. Okay, now that we know that 8 is basically the reference for convergence or not, we can say that, let's see what happens if a is less than 8, right? So if a is less than 8, we have that an will diverge to plus infinity, right? Because we have a power of 8 at the numerator, which is larger of any power at the denominator. So this implies that there is no necessary condition, so sum of an will diverge to plus infinity. If a is equal to 8 instead, what happens? Well, we have that an will converge to what? To 1, right? So again, we have no necessary condition, and we can conclude, because remember, the an has to goes to 0 in order to have the possibility for the series to be convergent. So again, we can conclude that an will diverge to plus infinity. Okay, now let's consider the last possibility, that a is less than 8. Remember that a is a positive number, so a will be any real number between 0 and 8. So can we apply the root criterion then? Let's see. So we want to study the nth root of 5 to the n plus 8 to the n divided by 2 to the n plus a to the n, right? But we can rewrite this as follows. This is the nth root of, well, we will factor out a to the n at the denominator, and we have 1 plus 2 divided by a all raised to the n, and we can factor out 8 to the n at the numerator, and we have 1 plus 5 divided by 8 to the n at the numerator. So if we extract 8 over a from the nth root, we are left with 1 plus 5 over 8 to the n divided by 1 plus 2 divided by a to the n. And notice that because we are now in a situation, sorry, this was a larger than 8, made a mistake. If a is larger than 8, of course we know that this, as n goes to infinity, will go to 0. This as well will go to 0. So this limit is simply 8 over a, that of course for a larger than 8 will be a number less than 1, okay? But if this is a number less than 1, by the root criterion, we can conclude that the sum of an converges. Exercise 5. Sum n goes from 1 to infinity of n squared plus 5 divided by n to the fourth logarithm of n plus n to the cube plus 1. Right? So once again we see that we have the sequence an, which is clearly always positive. Notice that this sequence is always positive as long as n is larger than 1. Okay, remember the diagram, remember the graph of the logarithm. Okay, in order to have logarithm larger than 0, n must be larger than 1. So we can say that this is definitely true definitively, okay, which what really counts, okay. And okay, but we need to check now if the necessary condition is verified. Now, what can we say when n goes to infinity? Well, clearly we can approximate an. The numerator will be asymptotically equivalent to n squared, and the denominator will be just n to the fourth logarithm of n, which is nothing else than 1 divided by n squared logarithm of n. And when n goes to infinity, this goes to 0. So necessary condition, okay. Still, we need to see what happens, okay? But now we have a good idea for Bn, right? So let's be formal and let's apply the asymptotic comparison with Bn equal to 1 over n squared logarithm of n, okay? And we are within the condition for the applicability of the asymptotic comparison, because an is larger than or equal to 0, bn is strictly larger than 0. So what we need to do now is to evaluate the ratio an divided by bn. Now an is n to the square plus 5 divided by n to the fourth logarithm of n plus n to the cube plus 1. And if we divide by bn, this is just like multiplying by n squared logarithm of n. Now let's proceed and factor out n to the square at the numerator. So we have 1 plus 5 over n to the square. And at the denominator, we will instead factor out n to the fourth logarithm of n. That will multiply 1 plus n to the cube plus 1 divided by n to the fourth logarithm of n. Right, so let's see what happens. And of course, all this is multiplied by n squared logarithm of n. Now, as n goes to infinity, this will go to 0, but also this will go to 0. Why? Because we have n to the fourth at the denominator, which is more powerful than n to the cube. So clearly this will go to 0. So this is now something that will tend to what? Well, let me write down here. This will be equivalent as n goes to infinity. Well, we can immediately see that n squared, let me change color, let me use the green, n squared, and n to the fourth will simplify, logarithm of n and logarithm of n will simplify, so this will tend to 1, but 1 belongs to the interval 0 plus infinity. So whatever the series sum of Bn does, well, the same the series sum of An does. Okay, so we are now within the condition of the asymptotic comparison. But the thing is that we still don't know what the series as n goes from 1 to infinity of 1 over n squared logarithm of n does. But we know that if we find this behavior, this will be exactly the behavior of the original series. Okay? Right, so we can attempt an asymptotic comparison with let's say another series Cn equal to 1 over n squared, which we know is a convergent series. Okay, so let's attempt this. So this time we need to write Bn over Cn and see what is the limit as n goes to infinity. So this is n squared divided by n squared logarithm of n, which is nothing else than 1 over the logarithm of n, and as n goes to infinity, this goes to 0, so we are in one of those limit cases. Remember that in this situation we have that Bn divided by Cn is definitively less than 1, which implies that the Bn is less than or equal to Cn. So if we have that Cn converges, and in fact we know that sum of Cn converges, this implies that sum of Bn converges. So the same thing can be concluded also for the sum of An. So we can conclude that the sum as n goes from 1 to infinity of n squared plus 5 divided by n to the fourth logarithm of n plus n to the cube plus 1 converges. Now there is also an alternative way to study the sequence sum of 1 over n squared logarithm of n, okay, as n goes from, let's say, from 2 to infinity. Okay, and what is that? Well, we can just make a pure comparison with 1 over n squared. So we can say that 1 over n squared logarithm of n, okay, well, this is less than or equal. We can build, first of all, this is always larger than 0, right? And but the thing is this, that we want also a fraction which is larger than this. To build a fraction which is larger, we need a denominator which is smaller. So we can compare this with 1n squared if logarithm of n is larger than or equal to 1. Okay, remember that this happens. This is the logarithm, right? So this is 1, and we want to have that the logarithm will be larger than 1. So if we are in this part of the real line, and indeed this is what we really are interested in, because we want to see what happens when n goes to infinity. Okay, so as long as this is verified, we can definitely say that this inequality is true. But now, of course, this will converge. This will give rise to a sequence that converges, to a series that converges. Of course, this will go to 0, and then this is, by pure comparison, another series that converges. Another interesting example is the following. Example 6. Consider this sequence, this series. Sum n goes from 1 to infinity of the logarithm of n divided by n squared. Well, in this case, of course, we have that an is larger than or equal to 0, notice that for n equal 1, the sequence is defined because you just have 0. Okay, so we know that the sequence has each and every term which is larger than or equal to 0. We also see that an tends to 0 because the n to the square wins over the logarithm of n. Now, we need to check, however, so we have the necessary condition for convergence, but we don't know if this series actually converges, okay? So we need to make some asymptotic comparison. Let's see what happens if we make a comparison with bn equal to 1 over n squared, because we know that the series of 1 over n squared will converge, okay? So well, of course, this is larger than 0, so both an and bn satisfies the conditions for the applicability of asymptotic comparison. So asymptotic comparison is related now to the limit of an divided by bn. Now, an is logarithm of n divided by n squared, and if we divide by 1 over n squared, this will be just like multiplied by n squared, and this is just logarithm of n. Now, the logarithm of n, of course, tends to plus infinity. So we are in one of the limit case. So remember that that implies that an over bn definitively will be larger than or equal to 1, which implies that an will be larger than or equal to bn. Now, the thing is this, that the partial sums, of course, we can say that the sum of an will be larger than or equal of sum of bn. But because the sum of bn, these partial sums, will converge, they will converge. Well, actually, we can't say anything about the sum of an. We would be able to say something if the sum of bn will diverge to plus infinity, because that will push the sum of an to diverge as well. But in this condition, nothing can be said. Okay, maybe the choice of bn equal to 1 over n squared was not the right one. Let me try with bn equal to 1 over n, okay? Again, this is larger than 0. So we can apply the asymptotic comparison to the, and we need to analyze the limit of an divided by bn, which is now logarithm of n divided by n squared multiplied by n. So this is the logarithm of n divided by n, and we know that this will tend to 0 because this is another limit case. And that implies that definitively an over bn will be less than or equal to 1, which means that an will be less than or equal to bn, and that implies that the sum, the partial sum of an will be less than or equal of the partial sum of bn, right? And now, once again, we are in one of the undetermined case, because we know that the harmonic series, well, this series will diverge to plus infinity, right? So this will diverge to plus infinity. So nothing can be said about the series of the an. So apparently, we need to stay between 1 over n and 1 over n squared. So let's try another sequence. Bn equal to, well, you see that we have made an attempt with n. We made an attempt with n to the square, so we would like to have the exponent of n to be somewhere between 1 and 2, right? So we can think of something like this. We can think of comparing the sequence with n 1 over n square root of n. Let's see, this is again strictly larger than 0, so we can do the asymptotic comparison now that will give an over bn equal to logarithm of n divided by n squared, and then we need to multiply by n square root of n, okay? And this is equal to logarithm of n divided by the square root of n. Well, but this, of course, will go to 0. So we are back in one of the limit cases, okay? And so again, we can say that definitively an over bn will be less than or equal to 1, which implies that an will be less than or equal to bn, which implies that the partial sums of an will be less than or equal of the partial sums of bn. But now the good news is that the sum of this series is a real number. So this basically is convergent, and this implies that this will also converge. Now, to prove the fact that the sum of Bn is convergent, let me rewrite this. So we have the sum, n goes from 1 to infinity of 1 divided by n square root of n. But this can also be expressed as sum 1 to infinity of 1 divided by n to the 3/2. So because 3/2 is larger than 1, we know by what we found last time regarding the harmonic series, we know that this is a convergent series. So we have solved the problem. Now let's try to understand more in detail why this comparison with 1 over n square root of n works. Okay, so if we have the real line, and let's say that we have 1 here, we have 2 here, and we have 3, right? And let's say, now, of course, we are considering the series of with the sequence logarithm of n divided by n squared, okay? Now let's consider these to be the exponent a, okay? So in other words, what I'm saying is that for a equal 1, we have the sequence, the harmonic sequence, 1 over n. For a equal 2, we have the sequence 1 over n squared. For a equal 3, we have the sequence 1 over n to the cube, right? Now, and we know that if a is 1 or it is to the left of 1, we have divergence. Okay, we proved that basically the generalized harmonic series diverges to plus infinity if a is less than or equal to 1. If instead we are on the right, okay, so if instead we are here for a larger than 1, we know that in all these cases we have convergence. So we can say that if we sit to the right of 1, we have convergence. Now the problem is that our series, which is logarithm of n divided by n squared, is not exactly any of this. We need to know exactly where this sequence sits, okay? Well, consider that logarithm of n at the numerator is consuming part of the n squared, which sits at the denominator. So if you like, we can say that the sequence logarithm of n divided by n squared is somewhere to the left, okay, of the point corresponding with a equal 2. Okay, so we can say that the exponent, okay, of the n of the harmonic series corresponding to that will be somewhere to the left of 2. So this is why basically the series converges. Okay. So in other words, we can say that this is just like having 1 over n to the a with an a which is between 1 and 2. So basically this will correspond to a point, well, to any point between 1 and 2, okay? And for example, I could pick this point, it would be exactly the same, right? So if I consider this point, it will be again a convergent series. Now, suppose that instead of having this logarithm of n divided by n squared, we had we had 1 over n squared, we had logarithm of n at the denominator. Well, in this case, we would be to the right of 2, okay? Because this would be equivalent to having 1 over n to the a with a larger than 2, okay? So we would see it somewhere here. And again, also in this situation, we would have a convergent series because we are in the realm of convergence of this series. So we have 1 over n squared logarithm of n. Example 7. Let's take the sum. N goes from 0 to infinity of 1 divided by 3 raised to the square root of n. Now, in this case, an, of course, this is larger than or equal to 0, so this is true, but also we have that an, for n that goes to infinity, goes to 0, so necessary condition, okay, so it is possible that this series will converge. But how can we prove this? Well, let's attempt just a pure comparison. We could say that 1 divided by 3 raised to the square root of n, okay? Well, 3 raised to the square root of n is less than 3 raised to the n, so we can say that this is larger than or equal of 1 divided by 3 to the n. And we know that this is now a geometric series with ratio 1/3. Okay, so we know that this is a convergent series. So this inequality doesn't help, okay, because we have that the larger part will converge, so we cannot draw any conclusion about 1 over 3 to the square root of n. So no conclusion with this. Okay, let's try now the asymptotic comparison. Okay, or we could basically, what we can say is that we know what is the relation between an exponential and a power of n. So we could write, for example, that 1 divided by 3 to the square root of n, right? So we know that the exponential is larger than any power of n. For example, n raised to the 2024, okay? So because 3 to the square root of n is larger than this, we could say that clearly this is less than or equal 1 divided by n to the 2024, right? Remember that basically the reason is that this is an exponential which is larger than a power. Okay, so this is the reason for having that. So it might be good at this point because we are now back to some generalized harmonic sequence. And what we could say is that we could attempt an asymptotic comparison with 1 over n to the 24. Okay, so we will try now to have an divided by bn. Now, an, of course, is 1 divided by 3 to the square root of n. And bn is 1 over n raised to 2024, so we have n raised to 2024 at the numerator. Okay? how can we work with this? We can transform this with the exponential. So we have e raised to the 24 logarithm of n, and instead at the denominator we have e raised to the square root of n logarithm of 3, right? And this is just like writing e raised to the 24 logarithm of n minus square root of n logarithm of 3. But we know that as n goes to infinity, this term, okay, will be dominated by the square root, because the logarithm is always lower than the square root of n. So we can say that this can be approximated as n goes to infinity to e raised to the minus square root of n logarithm of 3. And of course these limits is just 0 when n goes to infinity. So we are back into one of those limit cases of the criterion for asymptotic comparison. But what that means that basically an over bn will become less than or equal to 1 definitively, right? So this will be definitively less than or equal to 1, which implies that an will become less than or equal to bn, which implies that the sum of an will be less than or equal of the sum of bn. Now, we know, luckily, that the sum of 1 over n raised to the 2024 is convergent. And it is convergent because 2024 is larger than 1. So we can conclude now that because this converges, we can then finally conclude that the sum of an converges. We could have done, well, we might wonder, could have we done the same with the root criterion, because we have an exponent, okay? So we might wonder if that is possible. Well, let's have a go with this. Let's see with the root criterion. Well, remember that the root criterion is all about having the limit as n goes to infinity of the nth root of 1 divided by 3 to the square root of n, okay? Which is just like writing 1 divided by, well, we have the 3 raised to the square root of n divided by n, which is 1 divided by 3 raised to the 1 over the square root of n. And when n goes to infinity, of course this will tend to 1. And unfortunately, we cannot take any conclusion from this, because this was one of the undeterminate case of the root criterion. Example 8. Let's consider now the sum. N goes from 0 to infinity of n to the a time the sine of n plus 33 divided by n to the 5th plus 4. Okay? Now, what can we say about this an? Well, because we have the sign of course can be 0, okay, and can also be negative. So how can we make sure that this an is larger than or equal to 0? Well, it turns out that for n that goes to infinity, right, it happens that n plus 33 divided by n to the 5th plus 4, well, this will go to 0 plus, and this implies that, remember that when the angle goes to 0 plus, if you consider the sine, right? If you consider the sine of the angle, and if the angle goes to 0, from above, okay, goes to 0 plus, the sign will always be positive. So we can definitely conclude from this that an will be larger than or equal to 0 definitively. Okay, so this is enough for us for applying our criteria. Now let's have a first look at this an. Well, we can say that asymptotically an will behave like n to the a. So when the argument of the sign tends to 0, we know that we can approximate the sign with its argument. Okay, we can say that this is pretty much like n plus 33 divided by n to the fifth plus 4. But when n goes to infinity, this is just like saying na times 1 over n to the fourth, right? Which we can simply write as a fraction 1 divided by n raised to the 4 minus a. So because an does like this, it looks like just a generalized harmonic sequence, and we know that if 4 minus a is larger than 1, which is to say if a is less than 3, the series converges by just using what we know about the generalized harmonic series. Now, this was just first intuition about this thing. So we want to be formal now, and so let's prove this formally. Okay, the formal proof of this is that now, because our first draft, our first sketch, we know that the series that we want to use is the one corresponding to the sequence Bn equal to 1 over n to the 4 minus a. So let's make the comparison with this series, and let's see what does the ratio an over bn. Okay, now an is n to the a sine of n plus 33 divided by n to the fifth plus 4, and we need to divide this by 1 over n to the 4 minus a. And of course this is just like saying sine of n plus 33 divided by n to the fifth plus 4 divided by, if we just simplify n to the a, we just have 1 divided by n to the 4 here. Okay, and notice that when n goes to infinity, we know that basically this numerator, this will just tend to 1 over n to the fourth. So we can definitely say that this tends to 1, which belongs to the interval 0 plus infinity. So we are now in a good shape to apply the asymptotic criterion. So we know that whatever sum of Bn does, well, the same behavior will be the behavior of the sequence of the original series. And we know that this, of course, will converge for a less than 3. So the same thing can be concluded about the original sequence.